So today we will continue the discussion of input language of Clingo. So we'll talk about how to represent definitions in this language. What is a choice rule? That was actually a keyword today, and what are global variables and local variables. So after today's lecture, you'll probably see most of the constructs in this language. So if you want, you can start writing some simple programming too. Right. So this is what we were doing last time. How do we use intervals in the head? When you use intervals, you can actually abbreviate a lot of numbers there. So instead of writing this lengthy way, you can actually shorten this. The only thing that matters is actually the bounds numbers should be integers or something that can be evaluated as integers. You can write some arithmetic expression in place of these two numbers, but ultimately this should be evaluated as integers. Okay, and of course you have also learned another way to shorten it using so-called pooling, where you don't have to repeat the predicate symbol, but put the separator to be semicolon, so you have multiple elements that can be put together. Now pooling doesn't require to be using only for integers. It can be used for any symbolic constants as well. So that's a bit more general, but of course sometimes you want to prefer intervals because that is slightly better in some cases. Okay. So they have both pros and cons. Pooling can be used for non-numbers as well, while intervals can be better if it is about the numbers. Okay. So this was this is actually one question that we have. So if you see this one square of 1.8 and 1.8, what could be the stable model of this formula or this rule? How many elements are in the stable model? Can you guess? Square 1.8, square 1.8. So that has two arguments. Okay, the first argument can range over 1 to 8. Second argument can also range over 1 to 8. Okay, how many elements can be generated? 64, right? So let's check this because you can easily use Clingo to verify this claim. So I'm typing this thing. And as you know, okay, you can just type Clingo and the file name, and it generates this. As you see, it goes from 1, 1 to 1 to 1, 3 up to 8, 8. So it's all possible combinations of those 8 times 8 possibilities. So when you want to express some grid, this is actually handy, right? If you want to have this chessboard, like 8 by 8 chessboard, you can just write one line to generate all places in the chessboard. Okay, good. This is an exercise problem. I will not do it here, but you can always type in. And before you do that, try to gain insight. So what should be the stable model here? Okay, so think about it before you run it and check whether that matches your intuition. Okay, so definitions. We look at this small database before. We have parent relationship, okay? And we actually use this one to define child relationship, okay? Now let's do something else on top of this. So given this database, how would you define the predicate grandparents in terms of parent? How are we going to do this? Let's look at this together. So let's see, still the same thing. So I have 3 facts in my database. And I want to define grandfather. Who is actually grandfather of whom in this database? So Anne is a parent of Bob, Bob is a parent of Carol, Bob is parents of Dan. So what is the ancestor, grandfather parent relationship do we have?
Anne would be the grandmother of Carol and Dan.
Yeah, okay, good. So how do we express these things? So how do we write a rule that define grandparents in terms of parent?
Grandparent and Carol.
Grandparent and Carol. Like this. That is actually not bad. And if you ask Clingo, it will return the solution for you. But what if you have 100 parent relationship? Do you want to write 100 or even more than that? That might be a bit issue, right? Can it be a bit succinct? Can we define, I mean, grandparent relationship does not really depend on instance level, right? So what is the general thing that we say? If you know that X is a parent of Y and Y is a parent of Z, what can you say about X and Z? X is a grandparent of C, right? So that's what we want to write. So let's say grandparents of XZ, parent XY, parent YZ. Okay. Okay, so this is what I would write. Okay, so to tell Clingo, what do we mean by grandparents? So X and Z are in grandparent relationship, or X is a grandparent of Z, if X is a parent of Y and Y is a parent of Z. So let's actually check this. Okay, so in addition to the parent relationship that we gave, we also derived new relationship. So N is a grandparent of Carol, and N is also grandparents of Dan. So we achieved this thing. Good. Any question about this? Okay. The next question is, actually, we already did. So if you run Clingo, you will get this. Good. The next question is about the sibling. Okay. So let's go back to this thing. So we have N is a parents of Bob, Bob is parents of Carol, Bob is parents of Dan. Who's sibling to whom? Carol and Dan are sibling, right? But how do we tell computer about the sibling relationship? Let's actually forget about grandparents for now. So let me use the % sign to say comment. So Clingo will ignore this line for now. So we want to define sibling, but here sibling is like X and Y. We want this to be a sibling relationship. Okay? So how do we define sibling relationship? Oscar?
They have the same parent, so we would put in parent ZX.
Parents ZX.
And then parent ZY.
Parents of ZY. So when you read parents, who is parents? Z is a parents or X is a parent? Z is a parent of X. Yes. Okay, good. And Z is a parent of Y. Okay, good. Yes? Oscar, are you done?
Yeah.
Okay, good. So the idea is, this is interesting. He used the same variable Z to say that X and Y have common parents. Of course, sibling has common parents, right? Okay? So this almost work. Almost work. Okay, let's see what is going on. One nice thing about Clingo is you can actually run it to check whether this makes sense. What happened? Can you read what is there? What is wrong? So parent here, sibling. So Bob is sibling of Bob. Does not make any sense, right? You don't say that. Carol, okay. So this is wrong, but actually there's nothing wrong with Clingo, right? Because you, or Bob, has same parents as Bob, right? So going back to this thing that we did, if you say here, who was actually parents of so N is a parents of Bob, right? So Bob, if you replace X with N and Y with Bob, and I'm sorry, Z, sorry, let me look at this again. So if Z is N, and X is Bob, and Y is Bob, then this is true, right? So Bob and Bob are sibling to each other. There's nothing wrong with what Clingo will deduce from what you told, right? Why do we have Carol as a sibling? Because I think Carol has, Bob is the parents of Carol, right? So if Z is Bob, and X is Carol, and Y is Carol, then X and Y are sibling relation. So how do we correct this problem? So actually, I should say actually it's not entirely wrong because maybe let's go back to this again. It actually returns some correct one too. Dan and Carol are sibling to each other, right? And Carol and Dan are sibling. That's actually symmetric relation. That is okay. But the problem is we did get more than necessary, which we don't want to have. So how can we avoid that? Any idea? What is wrong with this thing, Ian?
We add rule into there where X is not equal to Y.
X is not equal to Y, yes. So we just want to prohibit that because now Clingo returns those things. If you say that X and Y should be distinct people, then you get these answers. That makes sense, right? Okay? So the nice thing about the Clingo language is it's interactive. So you can write the rule and then see if something is wrong with the output. Most of the time it's actually your problem. Okay? You did give wrong information, so Clingo had to compute that way. There's nothing wrong with what Clingo outputs in most of times. So it's actually your logic has a problem, right? You didn't include the fact that the siblings are about the distinct people, right? So we don't say X is a sibling of itself, okay? But you forgot to add that information, so that's why computer generates such a solution. Okay? All right. So in a sense, it's actually easy to debug. Once you write the rules, if maybe as a few weeks later, we'll do more bigger programming, just one rule or two rules. You may have to write maybe 4 rules or 5 rules. That's much harder than writing 1 or 2. Okay? But when you do that, try not to complete everything at one hand. Try to do this one by one and see whether the output of Clingo makes sense to you. Okay? All right. The next one. So here we have parents here. So before we get parents as a fact, but we can actually derive this fact from another relations. So if you know that x is a father of y, then you can say x is a parent of y. If x is a mother of y, you can also derive this. Now the definition here, the new thing is you don't need only one rule to define a new concept. You can have multiple rules. Okay? The idea is it's like a disjunction. So parents of xy, if either this or that or maybe both are true, then you can say that x and y are in parent relationship. Okay? And that makes sense to you too, right? Because father and mother makes parents. Okay, good. Now using this idea, we'll try to also think about ancestor relation. So ancestor is kind of grandparents, but it's more than that, right? So if you are parents of parents, then you are ancestor of that last person, right? And this goes recursively. So how do we describe this recursive definition? This is the rule, okay? So here we have x is an ancestor of y if x is a parent of y. Of course, note that you don't actually call your parent your ancestor most of the time, but according to the mathematical definition, you can say it this way, okay? Now, this is actually so-called base case. If x and y are in parent relationship, then x and y are in ancestor relationship. But there's also the recursive case. So we say that x is a parent of z if x is a parent, x is an ancestor of z if x is an ancestor of y and y is an ancestor of z. It's similar to the grandparents, right? But what is the difference? Main difference here. It's actually calling itself. When you define ancestor, you're calling ancestor again. That's the difference. Before, when you do the grandparents, so this was the grandparents on the left-hand side, and you have parent and parents, right? You don't call grandparents again. But in the case of this recursive definition, okay, the recursive definition means that you're calling the same predicate again. To define ancestor, you are using ancestor. Why this is okay? Because this is actually a shorter ancestor relation. Okay? So it's like induction that we studied. Induction can work out if this definition relies on the same definition but in a shorter or smaller relation. Okay? So if you don't understand that part, forget it, but it makes sense, right? So in natural language, in English, when you read it, that makes sense, right? X is an ancestor of z, x is an ancestor of y, and y is an ancestor of z. Okay? So you can run this on the Clingo, so let me not go over that part. Okay? The next one is about the prime number. Okay? So what is a prime? How do we tell Clingo to return the prime numbers? Prime is a good example of some interesting ideas of programming in Clingo. So in English, you can say that n is a prime if, actually I would say n is a prime between, let's say, 2 and 5, just to show that the output is simple to look at. You can change 5 to any number n that you want. For this time, let me just talk about prime number between 2 and 5. Okay, there are 3 prime numbers, 2, 3, and 5. How do we return all these things? So by definition, prime number says if n is one of the numbers 2 to 5, okay, and there is no evidence that it is composite. What is a composite number?
A number where it has factors other than itself and 1.
Right. So numbers that have factors other than 1 and itself. So this definition here is actually using composite. We didn't define composite yet. We are going to do that based on what Matthew just described. But if you look at the English statement, this is what we can write. So n is a prime if n is between 2 and 5 inclusive and is not a composite number. So look at this. This English description is more like one-to-one translated into this rule. Okay? how do we define composite? This is actually very interesting, and maybe a bit of hard to understand in the first sight. So suppose you want to write a Python function to check some number is a composite number. What would you do? Well, you have to enumerate from numbers from 2 to n minus 1, right? So let's actually see how can we do. So if we want to say whether 5 is a, so let's say 4 is a prime number, 4 is a composite number, okay? How would you do that? Okay, you write a for loop, right? And check whether, so for loop starting from, let's say, 2 until 3, right? Because those are the numbers that is not 1 and not 4 itself, right? So you have to check basically whether 2 divide 4 or 3 divide 4. If one of the check is true, then 4 is a composite number, right? So in general, if you want to check whether n is a composite number, you have to check for I equals, say, 2 to n minus 1, okay? Check whether whether n is divisible by I, okay? If yes, then you stop. I'm not going to write the full algorithm, but you can get it, right? So from 2 to n minus 1, if at least one of them, one of these smaller numbers divide n, then n is a composite number. Okay? So is 5 composite? No, because according to the algorithm, you check whether 5 is divisible by 2, no. 5 is divisible by 3, no. 5 is divisible by 4, no. Okay? So none of the numbers from this range can divide 5. So 5 is not a composite. And 4 is composite, as we just talked. But how do we write these for loops in Clingo? This is the rule. And as you see, there is no for loop. Just one line. How does it work? Well, I want to check whether n is a composite number. Okay? So n actually ranges over 1 through 5. So let's say pick n to be 5. Okay? So I want to check whether composite of 5 is true. Then that's same as checking this one. When n equals 5, I can range from 2 to n minus 1 or 2 to 4, and n is divisible by I. If this condition is true, then n is a composite number. Let me repeat. Fix n. I fix n to be 5, okay? Then I ranges from 2 to 4. And this check is doing that 5 is divisible by 2, 5 is divisible by 3, 5 is divisible by 4. If any of them is true, then this becomes true, so 5 becomes composite. If none of them are true, then composite of 5 is false. Okay? And that's whole code. Think about what would you do to generate prime numbers from 1 to 1,000. How many minutes do you need to solve that problem? So let's actually look at this. Okay, so if you see the last two lines here, so this is the same program that I showed you. Actually, I placed n here, so let me actually. Okay, so before we had 5 here, but I just replaced with n, which is a placeholder. So I'm going to use this program to generate as many prime numbers that I want. So minus c n equals, let's say, up to 100. How many prime numbers are from 1 to 100? No? You don't know? We can count. Okay, so, okay, this is it. Okay, this looks actually quite complex because we also say composite. So if you look at the output, we actually tell Clingo also to talk about the composite numbers. So 4 is composite, 6 is composite, 8 is composite, 9 is composite. And at the bottom, you see that prime numbers here. Okay, so 2 is prime, 3 is prime, and so on and so forth. Okay, of course, you can suppress the output of these composite. How do we do? Do you remember what we did? Yeah, we use directive show prime. Okay, and if I do this, I get only prime as output. Okay, good. Will it be much hard to compute 1,000 prime numbers? No, it takes 0.009 seconds. How about 10,000? It took a bit longer, but still 0.4 seconds. Not too much. Yeah?
How would we count how many prime numbers there are?
Good question. There is a count aggregate that we are going to talk later. Okay, I can show you maybe if you're interested after the class, but that will come maybe 2 classes after. Okay? Good. Fibonacci numbers. Do you recall Fibonacci numbers? You should, right? We had many exercise problems on that. So how do we describe Fibonacci number? What is Fibonacci number 0? 0. Fibonacci number 1 is 1. Fibonacci number 2 is fib of 0 plus fib of 1. So that's a recursive call. So this is how you define Fibonacci number. Fib of 0 is 0. So we are going to use this predicate fib of I comma m to denote that I Fibonacci number is m. So when I say fib of 0 comma 0, this is a fact. We tell the Clingo that 0's Fibonacci number is 0. And same way, the next Fibonacci number is 1. Okay? Now after that, we can say fib of n plus 2 is defined by 2 previous Fibonacci numbers. So here, let's look at this. If nth Fibonacci number is f1, and n plus 1 Fibonacci number is f2, then the next Fibonacci number is f1 plus f2. Makes sense, right? You just add 2 previous Fibonacci numbers to generate the next one. Okay? I used this one because I want to generate Fibonacci number up to 0 to nth, right? Otherwise, Clingo will have to generate infinitely many prime Fibonacci numbers, and that is not possible. Okay, so this one tells me that n plus 2 here will range from 0 to n. Okay, so let's actually look at the fib. So this is the program that you saw in the previous slide. Okay, and then let me just copy it here. Okay, so this is 1. And you can say Clingo, let's say maybe up to 10th Fibonacci number. Okay, so this is the output that you get. As you see, 0 is 0, 1 is 0 plus 1 here. 3 is 1 plus 1. 4 is 1 plus 2. And the next is 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8. So that looks correct, right? So as long as you give the correct input, Clingo will say the correct output. Okay? So this could be a good practice tool for you to start to practice logic. Okay? You have logic in your mind, but there may be some bugs, right? So Clingo will help you to identify the bugs, and that will help you to also gain some insight. Now let's talk about factorial. Factorial is also a recursive function, right? So n factorial is defined as n times n minus 1 factorial, right? So when we say f of m, this is m times f of m minus 1. So to define factorial, we call factorial again. So that is the idea. Okay. So this is the factorial program. Okay, so fact of 0, 1. So the first 0 factorial is 1. So that's what the first line is saying. The next one is n plus 1 factorial is f times this. Actually, let's read from the body. So here n goes from 1 to n. And nth factorial is f. Then n plus first factorial is f times n plus 1. Okay? So f is the previous factorial, okay, on n factorial. And then you multiply next one, n plus 1. Are we together? Okay. Any question? N plus 1 factorial is n plus 1 times n factorial. That's what the second rule is saying. The next line is kind of projection. I just want to know the what are the factorials. I don't need to remember the first argument, so then you can use the last rule here to project, to forget about the n. Okay. Maybe let's actually talk about, let's actually do this. And then I only say that show only the factorial. Okay. Will it run? Does it make sense to you? Let's play this. I will say maybe first 10 factorial numbers. Oops. What is wrong? I got only the first factorial. Why? Let me just show this again. So this is the program. This program, I inserted intentional bug here. Okay, so what is the bug? This could be a participation credit problem. So if you get it right, you earn the credit. What is a bug in the code? Okay, so I told you that n 0 factorial is 1 and n plus first factorial is n plus 1 times f, where f is the nth factorial, right? So why it does not return all the factorial? Oscar?
Is it because since it's from 1 to 10 and in the head it says factor of n plus 1, that's over the range?
Which part are you saying?
Oh, since you put n equals 10, right? And then
N equals 10, yes. So this n is 10, yes.
And then in the head, when it says fact n plus 1, that is over the range? Is that why?
Well, then it should return 11s, right? But I didn't see anything about that. 11 it's only showing one factorial, not the 11th factorials. So, yeah. You both have the participation credit, so maybe can you just wait for a moment? Anyone who didn't have participation credit yet? Yes. Fact 01? Yeah. Yeah, what is wrong is this?
Well, isn't it limiting? You're only going to do 0 to 1, then like it'll only show 0 to 1?
Yeah, that is why fact 1 is shown, yes. But why this one does not work? We want to generate more factorial, like a Fibonacci numbers, right? We want to generate more, but why is only showing 1? Why not the next factorial? Why is not showing? Why is not showing? So maybe, I don't know whether how much this will help you, but let me just suppress all the other features that we don't need. Okay? Okay? So just look at the two rules. Okay? Hint, the first rule is okay. Second rule is the problem. But what is that problem? Let's actually execute this again. Yeah, still we got fact of 0, 1. Okay, that's the first rule. Right? Okay, now let's see. Matthew or Nathan, who raised first?
I actually thought it was in the other line. So.
Okay, so then, how about Nathan?
Because you don't define what f is.
What f is? No, f is actually here.
But okay.
You can. N is starting from 1. That's the problem. Why? If n is starting from 1, fact of 1 is not defined before. There's no base case. Nothing can actually derive new information. Okay? So maybe let me just use that correction, and then we'll come back to this. So what Yukon is saying is the problem is actually the range. It starts from 1. So let's start from 0. Okay? And then let's call, okay, this is the modified code. Okay. Okay, now you get it. So let's read this again. So this time we have factor of 0, factor of 1, factor of 2, and all true. This is similar problem as you met in the induction. Okay? There is a gap in the induction proof. Same thing happens here. Okay? When n starting from 0, you can say since fact of 0, 1 is true, fact of next one, which is 1, fact of 1 is 1 times 1. So you get the next one. Okay? But if n starting from 1, then you cannot use the base case because fact of 1, f is not defined. Okay? The error was here. You cannot start from 1. You have to start with 0. Okay? So second rule was not used at all when you say that n starting from 1. That was the problem. Okay, good. So just recap. This will generate many factorial of binary factorial predicate. But if you want to know only the factorial numbers itself, then you can project it and show only these things. Okay. All right. Next concept is choice rule. So, so far, when I run the program, there was only one stable model. But this is not always the case. Now, starting from here, you will see that the Clingo may return multiple stable models. Okay? And that has to do with this construct that we call choice. So here we use the set trace, okay, to say that there are two elements in this set. And when you call Clingo with this program, Clingo will try to find all subsets of this program. How many subsets are there? 4, right? Empty set or two singleton sets and the total set. There will be 4 stable models. Okay? Okay. Now, what is the intuitive reading about this rule? This rule is saying, well, choose arbitrarily among these elements among this set. Okay? Among the elements of this set, just choose arbitrary. So you can either choose P of A or not. So there are 2 choices. And Q of B, you can choose Q of B or not. So there are 2 choices. So there's 2 times 2 choices possible when you select some members from this set. And you can also write the choice rule with the pooling and intervals. So this is the pooling that you saw. And the pooling simply generates multiple predicate, right? So how many? So this one has the same meaning as choosing one out of these, choosing one subset or any subset of these choices. So how many stable models will be there? Okay, if you're not sure about what I'm saying, let me just go back. So what I was saying is, suppose you have 3 elements in this set. Okay, if you call Clingo, it returns multiple answers. Okay, so the first one is actually empty set, and you have singleton sets here, and double element set here, and then total set here. So there are 8 subsets of this. Okay, so if you have 3 atoms here, then you have 8 choices. Okay, so empty set or singleton set, and 2 element set or 3 element set. If you count everything, there will be 8. Same here. So P1.3 has the same meaning. Okay, this is an interval, and it has the same meaning as 3 elements here, and it will also have 8 stable models. Now, when you call Clingo, if you have noticed, I typed a 0 at the end of the command line to ask Clingo to return all stable models. And we can also use the integer bound in this set. So here is an example. Okay. So without this 1 and 2, how many stable models were there? There were 8, right? But with this one, now we are saying, we are asking Clingo to find the subsets of P1, P2, P3 that contains at least 1 element and at most 2 elements. So we are only interested in the cardinality, which is greater than or equal to 1 and less than or equal to 2. So how many stable models will be there? If you ask this one. So you ask Clingo to return subsets of P1, P2, P3, but the cardinality should be greater than or equal to 1 and less than or equal to 2. In other words, you are eliminating empty set and the total set. So how many stable models are there? 6. Okay? So let's check that claim. It's not exactly the same, but example, but structurally same. So let me just use this one. So I asked Clingo to return the subsets whose cardinality is within this range. Okay. So this is the program, SS. And then I put 0 to ask Clingo to return all answer set, and they're all stable models. So there will be 6 stable models here. And as you see, empty set is not there, and total set is not there, because they violate this cardinality constraint. Okay, so here is an exercise problem. Okay. How many stable models will be there? So this is this one program, so it has 2 rules. Okay, participation credit. Who will answer this question? Yes. 60?
16.
16. So what is your reasoning?
There are 3 elements in P, so just 2 to the 3, which is 8. And then Q has 3 elements, 2 to the 3, which is 8, and then add those 16.
8 plus 8 is 16.
Yep.
So if you look at this one, I see that there are 8 possible choices, right? And also 8 possible choices. So when you add up, it's 16. Okay. So let's check that claim. So P1.3. Okay, so this is the program. So let's ask Clingo to return who? What is this? I had a typo. I didn't close parentheses. Okay, so let's say 64. Almost there, except 8 and 8, you have to multiply because those are independent choices. 8 times 8 is 64. As you see that, yeah, you select any subset of one of them, right? Okay, so let's say P1, P3 is subset of the first one, and then you have Q2, Q3, subsets of another one, and that's a all combination. So 8 times 8 is 64. Let me give you one more credit problem. It's similar, but a bit different here. Again, open to people who don't have participation credit yet. So how many stable models will be there for this second one? Okay, just wait for a moment. Let me give you maybe 30 seconds. Ziad, do you want to try again? 16? 16? Anyone else? Daniel? 2 to the 9th. 2 to the 9th. 2 to the 9th is 12. Did you really count all 512? No. How did you come up?
So I was thinking, so if we, since there's 3 for the first parameter, 3 for the second, 3
Uh-huh.
times 3 is 9.
Uh-huh.
And the power is set, the power set.
Correct. So what he is saying is the rule inside will generate 9 atoms. So P 1, 1, 1, 3, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3 will be generated here. That's 9 atoms. And you have looking at the subsets of 9 atoms, that is 2 to the power of 9. So let's actually check it. $512. Okay, good. All right, so I have next problem, but we're not going to discuss here. You can try to solve this exercise by yourself, or we can go over this in the recitation sections. Okay? All right, so we covered until the choice rules, and then we'll cover more next time. Okay, so this is for the lecture today, and we'll start the quiz soon. Any question up to here? Okay. Okay, so close your notebooks.